Hello again. So now the next lecture is about basic number theory. Let me share my screen. Here we are again. And we're going to do some modular arithmetic. Now you know that integers are whole numbers, yeah, like positive and negative, and 0 is an integer too. Primes are special positive whole numbers that are only divisible by 1 and of course themselves. So 2, 3, 5, 7, not 8, not 9, not 10, 11, 13, 17, 19, etc. Okay, those are primes. Now we're going to use this notation brackets m comma n, close brackets, this notation here. That's the number of common factors that two positive integers have. And if they only have one in common, it's the only thing that if one is the only number that divides m and n, both of them, then they are called coprime. So for example, 3 divides 15 and 3 divides 21. So they're not coprime. 1 and 3 divide them both. So this is 2. What about 5 and 22? Well, they're coprime because 5 is a prime and 22 isn't a multiple. So mn is 1. 18 and 35. 18 is 3 squared times 2 and 35 is 5 times 7. So these are coprime as well. Okay, so that's what I mean by coprime. Euler's totient function is this phi, capital Greek phi, brackets n, which is the number of integers that are coprime with n. Let's have a few other examples. I've written some here. So let's take phi of 9 equals, well, 9 is 3 squared, so obviously 1 is coprime with 9 because 1 is coprime with everything. 2 is not, it is coprime with 9, 3 is not, 4 is, 5 is, 6 is not because 6 and 9 have 3 in common. 7, yeah, and 8. These are the numbers that are coprime. And this long line here means count the number 1, 2, 3, 4, 5, 6. So phi 9 is 6. Now, looking at this slide here, phi 7 is, well, obviously 1. No, 2 doesn't have a factor in common. In fact, not, because 7 is prime, you get all the numbers less than 7. And more generally, when you've got a prime number, the Euler's totient function is 1 less than that number. So now we'll do some more. Mod 6. And instead of equals, we use this, actually it's called congruent to, that's how you pronounce it, congruent to. So that's the notation. So we go round this way. 1, 2, 3, 4, 5. Hang on, we have to go around 5 times and we get back to here at 6. So it's 1, 2, 3, 4, 5, and then 6. No, it doesn't. It goes back to 0. I was corrected. 1, 2, 3, 4, 5, 6, and 0 is the same. and then 7, 8, 9, 10, 11, same as 0. Okay. So what I can write is, for example, 12 is congruent to 0 mod 6. What about 14? That's congruent to 2. Keep going around and you get 13 congruent to 1, 14 congruent to 2. More generally, what about 27? Congruent to, well, I just go up to multiples of 6. So I can get up to 24, that leaves 3. More generally, actually, if I did this number, 27 minus 3 equals 24, is equal to 4 times 6. What this means is if you've got two numbers like A and B, congruent mod 6, it means that 6 divides A minus B. And it doesn't have to be just 6, it could of course be n, any number, any positive integer. All right. So here are some examples. We can have negative numbers as well, they don't have to be positive. So for example, minus 2 minus 3 is minus 5. Minus 2 and 5 divides minus 5. It's 5 times minus 1. This minus 10 minus 4 is minus 14 and so forth. Okay, now here's an exercise. Let's work out the following. 7, congruent to what mod 11? Mod 11, 7 is already in the first round, so 7 is just congruent to 7 mod 11. But what about 49, 7 squared? 49, well, 4 11s are 44, so that leaves 5. 343, my 11 times table is not very good. I'm going to need a calculator. So, where are we? Here's a calculator. Can you see that? Oh, you can, good. So, 343 is 7 cubed. So, let's do 343, divide it by 11. So that's 31.181818, okay. Well, it's the bit less, after I've gone 31 times round, I go back to 0. So I'm only interested in what comes after the decimal point. So let me take off the 31. Okay, so if I multiply that by 11, I should get a whole number. Yeah, 2. Okay, so I think it's 2. Let's just check. So what is 343 minus 2? And then if I divide that by 11, yeah, good. So there is a way I can work it out. What's the next one? 7 to the power 4. Oh, okay, so hang on. 7 times 7 times 7 times 7 equals, that's that. Divide by the modulus, that's 11. Okay, take off the whole bit. And now go back, multiply it back up and get a number. 3, okay. So 7 to the power 4 is congruent to 3 mod 11. And I can go on and on and on, and I can get up to 7 to the power 10, congruent to what? I don't know. It'll take a long time. But notice that these are, so far at least, they're all different. So I wonder if I'm going to get another different one here, like 4 or 0 or whatever. It would be quite interesting to see. Now, let me just go back to me for a bit. Probably need to go back to the webcam again pretty soon though. Right, so let's work out these values for this particular interesting to the power, you know, like 7 to the power 3 mod 11, what is it equal to? Well, we know how we can work those out. I'll just do one of these and leave the rest of those to you to sort out. So back to the webcam. Let's do M is 11. M is 11. E is 2. Mod 17. What is it? So 11 squared is congruent to mod 17. What is that? Question mark. I'll get my calculator again, quickest. Hang on, message from the builder. I'm absolutely inundated with builders. Sorry about that. Now, the calculator is here, and 11 squared. 11 times 11 is 121, and it's 17. Divide by 17. Okay, take off the 7 and multiply by 17. 2. The answer is 2. And so we know how to work them out. That is really the point to make. But the other way around, let me see if I can do the other way around. I know, don't know M now, but I know C. So it's something to the power 2 is congruent to 10 mod 13. No, yeah, mod 13. Okay. So there isn't a way to calculate it. I just have to do it by trial and error. And I'll probably get there in the end because I'm just illustrating this with some very simple integers, small numbers. But actually, in cryptography, for blockchains, we are working with massive products of, you know, millions of primes. Well, maybe not millions, but, you know, thousands of primes, and they're all in hexadecimal. We don't use integers. We do the same arithmetic, but with hexadecimals, and it would just be impossible. Okay, this is called the discrete logarithm problem, and oops. We've just seen it in action. It's almost impossible to find this number here, M, when this is very large. It's called the discrete logarithm problem, and that is the basis of what we call RSA encryption, which is a way of generating public and private keys. So if you've actually tried to get a wallet, you will be given a public and a private hexadecimal number. The public one you can give to anybody, say, you know, I'm going to send you this money, here's my public key. Well, actually, in most, you normally send a hash, but that's something I'll get onto in the next topic. With these keys that you generate, you need to use this theorem, okay, in RSA. So, sorry, here's a theorem. For any positive integers m and n that are coprime, m to the power of the totient function is congruent to 1 mod n. So let's have a look and see if it works. On these numbers, 9 and 5. So I need to find phi of 5. Now 5 is a prime number, so we know it's 4. It's always 1 less than the number if the number is prime. And so 9 to the power 4 is what we need to find and show that it is congruent to 1 mod 5. Okay, so that's the calculator. 9 times 9 times 9 times 9. That's 9 to the power 4. And then divide by 5. Take off the 1, 3, 5, 2, was it? Messed up, actually. Let's start again. 9 times 9 times 9 times 9 equals, that's right. Well, actually, I know that it's going to be congruent to 1 because 6560 is obviously a multiple of 5. So, yeah, when I divide by 5, I'm going to get 1/5. 0.2, and then 0.2 times 5, of course, is 1. So there we are, we verified it. And you can also have a look at these other exercises I've given you to make sure that you understand this theorem. And finally, we're going to revisit this 7 congruent to 7 mod 11, and then all the powers of 7. 7 to the power 4 congruent to what? 7 to the power 5 congruent to what? Now, I asked the question whether with all these numbers here, we'd never get a repeat until we get to 7 to the power 11. And that would make 7 a generator of 11, of modulo 11. Here's another example. 3 is a generator modulo 7. Why? Because when we take the powers of 3, mod 7, we get 3. 3 squared is 9, which is congruent to 2. 3 cubed is 27, which is congruent to 6. And 3 to the power 4 is congruent to another different number, 4 and 5, and eventually we get to 1. So that when we go again, 3 to the power 7, we would get back to 3. And we'd cycle around like that, 3 to the power 8, 3 to the power 9. It's called a generator, also called a primitive root. So formally, G is a generator, modulo n, if for every number here that is coprime with n, and in particular that will be all the numbers less than the prime number, because all numbers less than a prime are coprime with it. We get a different one when we raise G to some power B. So we're going to use the idea of generators in the next lecture when we get on to key generation and encryption algorithms. So that's it for now. And I'm very glad I finished the video in time to answer the door to the builder. See you soon.